We like to record this. We record this for the our website so that people who couldn't come today could listen to our presenter. So if you don't want to be seen on camera, you can turn off your video and that'd be fine. So we'll talk a little bit about our program for the upcoming few months, and Swapna and I have been working, and Anil actually has been helping us out, our treasurer, as a honorary member of the program committee, coming up with some great presentations for the fall. And one sort of unexpected offshoot of the whole COVID thing is the introduction to inviting people from far and abroad to present. And we've had presentations from as far as, well, we've had someone already from CFHT, Mary Beth, a few months ago, and now with Dr. Rousseau-Nepton, we've had people from as far away as Florida present to the center, which is great. So I think it'll be a nice combination in the future to bring in people from far and abroad, but also some local speakers. Okay, so I think I'd like to start the meeting. So generally this is a speaker's night, and what we do is we invite a speaker to give us a talk on their area of expertise and research. And we've had some really interesting presentations over the years, because it's really interesting to get an update on a researcher's up-to-date results and even their future goals in using various instrumentation, whether it be on the ground or in space. And I know everyone is looking forward to the next big space telescope, James Webb, in the next few months. But today we're focusing on the Canada-France-Hawaii telescope, which I remember back in the late 70s was an amazing thing that opened up and offered great opportunities for Canadian astronomers to have access to a world-class instrument. And the neat thing about observatories and telescopes is, and very much like not only on the ground but in space, all know that Hubble has been visited several times and upgraded. And ground-based telescopes are always being upgraded with new technology and sensors and various instrumentation. And it sounds like the work of our speaker tonight is based on the use of some new instrumentation on the Canada-France-Hawaii telescope. So with that, I would like to introduce our speaker, Dr. Laurie Rousseau-Nepton, who is a Canadian from Quebec, and has been working on the mountain, or the extinct volcano in Hawaii, for over 4 years now. And I think it's interesting that she is the first Indigenous woman in Canada to obtain a PhD in astrophysics, and this is the kind of thing that we all want to see more diversity in the area of astronomy research. So I think we're all honored today to have Dr. Rousseau-Nepton as our guest, and I'll ask Laurie to take over and share the screen and talk to us about learning about the birth of stars with SITELLE, I guess. Hopefully that's the right way to pronounce it. So Laurie, yes, the floor is yours.
Thanks a lot, Randy. It's my pleasure to be with all of you guys today. So I have prepared a presentation, and I'm going to share in a few seconds for you today, showing you a little bit where I work, what I do, and slowly introducing my favorite topic, how the stars were born in galaxies. We're doing a lot of research at CFHT. I am lucky enough to be working with the instrument that I've participated in building in Canada, and then we shipped it to Hawaii. And I'm currently leading a program with it that really benefits from its capabilities. So the instrument was essentially built to do those kinds of research, and I hope I will be able to convince you of that today. But it can do so much. So I'm going to start sharing my screen. Hopefully I'll get it on the first shot. And by this time, or about this time, you should see my slide. I hope it's working. And if at any point during my presentation you have questions, feel free to interrupt me. I won't be mad at you. I really like answering questions where they are alive and exactly the topic that I'm talking about. But you can also wait until the end. That's fine with me.
Laurie, I think what we've done in the past is we've asked people just to enter questions into the chat.
Into the chat. Okay, I'll try to keep an eye on it. If there's a question in the chat, then
if you want to, that's fine. But if you want to go through your presentation, it's up to you. I mean, I don't want to dictate how you do it, but
no problem. I'll keep an eye on the chat, knowing that you work with that. It's perfect with me.
Yeah, we can go through the chat after the talk. I think that works well. But again, whatever you're comfortable with.
Okay. That's perfect. Okay. So I might catch your question in the chat if I see it then. So I'm an astronomer, a Canadian resident astronomer, the Canada Friends Hawaii Telescope. I've been here for 4 years and a half now. And I'm originally from Quebec. I did my bachelor, master, and PhD all at Laval University. And this is a picture of me back then when I was with a crowd of students from Quebec in one of our meetings. And being issued from Canada, I've learned a lot in doing observational astronomy because we are lucky enough to have training facilities such as the Mont-Mégantic Observatory. And I was there a lot, observing with different kinds of instruments, starting with imaging cameras in the visible to spectroscopy with long-slit spectrograph, all the way up to doing infrared cameras, and of course, my specialties, the Fourier Transform Imaging Spectrograph. At Mont-Mégantic, we had a prototype called Espion that I used for my master and PhD, and I learned to use it. I updated how we use it and optimized the way we do calibration and analyze data with it. And this led me to building up expertise in observation. I love observational astronomy. And so once I was doing my project with Espion, with Carmel Robert, and also the team of Laurent Drissen, who was building it. This is the beast right there on the telescope. So I built that expertise, and of course we went through building another one that was bigger, better, and for Hawaii, for a bigger telescope, which is called SITELLE, the one that I work with right now. So it really helped me qualify to get hired to the position I am right now, and I'm really thankful for that. We were talking about weather and storms before I started my talk. I just added that slide when you guys were talking, because this is a picture of the first flight of SITELLE in Hawaii. It was just before I graduated, and we were in the control room, looking at the monitors, and really angered to see the first data. And back in the days, I remember very well, there was a hurricane called Guillermo that was literally rushing to go through the islands, and we got lucky enough so that Guillermo just decided to go north completely out of nowhere. And instead of hitting the islands, we had 7 nights of perfect clear weather to do our first flights. So I was really happy. And this is one of the first objects we observed. It was a planetary nebulae. But I was more interested in that very small galaxy in the background that I was analyzing as I was sitting right there in the background. And I was able to, of course, get velocity curves and metallicity plots of the galaxy very quickly. I was super excited about that. And so this was the start of the instrument. It's been at the telescope for about 5 years now. We have improved it. We have helped a lot of people to use it. And now I'm doing a much larger program with it that I'm going to talk to you today, Signals. So after my graduation, I was shipped to Hawaii to help with SITELLE, and I've been here since then. Well, for those of you who don't know necessarily the island, so the big island of Hawaii is the largest island of the Hawaiian archipelago. And it, of course, has active volcanoes. I've learned that very quickly when I moved here. After 1 year, we got one big eruption, which led to some issues with data. We got some sulfuric acid to monitor during the day and, of course, at night. Those gas can be dangerous for the mirror of the telescope. They can degrade the coating of the mirror. And so we had to implement some method to measure the amount of gas in the atmosphere while we were observing. And it became a new reason to eventually close the dome in some situation. Fortunately, it didn't happen too often. But the Mauna Kea is a beautiful site. So the Mauna Kea is the largest mountain on the big island of Hawaii. Yes, we do have snow here for about 3 months a year, from December to February, more or less. And as you can see on that image, we are also most of the time above the clouds. So we have really good condition for observing. About 75% of our time is clear for observation. So very efficient way to use the sky. And this is a picture from the other side of the mountain during another season from the Mauna Loa, just to give you an idea of the site. There's a lot of other telescopes on the mountain. We have 13 facilities, 12 of which are still active. And the CFHT, which you can see at the center here, is, to my opinion, located at the best spot on the mountain. And mountain can also be in the clouds. And since we were talking about hurricanes and stuff, this is an image, a video actually, of lightning that hit another telescope right beside CFHT, the Gemini telescope, our closest neighbor. And we are actually connected to the Gemini telescope with a long fiber optic that connect basically our Herschel spectrograph to their 6-meter mirror. And because of that, we had some issues related to that lightning strike, actually. And we had to fix some of the system in the spectrograph because of it. So we always have to be ready for any eventuality up there. But it's a beautiful site. And this is the mountain. The mountain, the Mauna Kea, is also a sacred site in Hawaii. We've heard of it multiple times in the news in the past years. There've been some protests on the building of the 30-meter telescope that was very, very often making the first page. And we are also working with the respect of the land and in collaboration with people in Hawaii to make sure astronomy is done the right way, and also considering how they want us to use the land and participate in this endeavor of doing science up there. So I feel really privileged to be able to give this talk today because I'm using data from the Mauna Kea. I'm working on the island and working at a telescope that is located also on the Mauna Kea. Yeah, some people who are also there during the hurricane. We made it. In 2018, it was a bad year for hurricanes. We got a couple of them. So yes, it's a beautiful site, and astronomy is also always using sight on very large mountain high up, and they are often sacred sites. So it's something that is part of what we do, and we always have to keep that in mind when we work. So now let's jump into the telescope. This is the CFHT with our dome bands, and if we jump into the building, this is the telescope. A view from the top and here from the side. So just to give you an idea of the size of it, I have some of my colleagues that are on this picture. And of course, I like to show things when they are in motion. I hope you would be able to visit it in person because it's absolutely gorgeous. But the dome, sometimes we can have people also see when it opens, when the dome bands open just early in the night when the sun is setting. and just to try to thermalize the area. And of course, I'm gonna go a little bit further in that video just to show you a little bit of motion and eventually just to glance a few seconds at our mirror. It's a 3.6 meter mirror. Yes, it's gonna start in a few seconds. There you go. And at the very end, we'll see a little bit our mirror. Our mirror, we do the recoding of the aluminum surface to make sure it's very reflective every 3 years. We did it actually during COVID. It was a challenge, but we made it in 7 days. And we have all the needed equipment to do it on site. So we also do the coding of other telescope on the mountain on the Mauna Kea because of that, which is pretty cool. So now we're gonna jump into science. And before I go into what I do, I always do a very quick review of what led me to do that research. And I know most of you are probably aware of all of this, maybe some are not. I heard that some people from other departments might join and students as well. So just to make sure that everybody is following me through the science. And of course, we're gonna get to deeper and deeper as I go until the end of my presentation. But this is a very known image, the Hubble deep space, and we see all these galaxies and all these shapes, colors, and of course some are closer, some are further, and of course using spectroscopy we can get estimate on their distances, and we've built a very different image of the universe around us since we've access to these data. So it's both imaging and spectroscopy that really led astronomy to understand the current state of our universe, and since the Big Bang, right? And my specialty, what I observe is really in the local universe, but since the Big Bang, the first few billions of years, the first structure that formed and how this universe evolved through time, we really have a lot of changes to study. And in astronomy, it's about understanding those changes and maybe eventually know how these changing are going to apply in the future of the universe. And so for me, it's important to just remember that and dive into those first sequence where the universe was born into that soup of particles that eventually cooled down and became into some state that enabled structures to form and eventually stars to get formed as well. And what I like to think about is, of course, when the stars started to form, and we can kind of imagine that although we cannot see how those first stars were, what they look like, and how they contributed to changing the image of the universe and what it was back then. But they were formed with the soup of atoms that was generated right after a few hundreds of millions of years after the Big Bang. And they were very different than the stars we know today. They were, as I heard from many studies, most likely very massive, and such massive stars don't exist anymore, or at least they could be as massive as a few hundreds to even, I heard, 1,000 solar masses. But anyway, we can keep that in mind, you know, that those stars really influenced the chemistry of the universe. And also they were inside those first galaxies that were at the same time organizing the matter and forming. And as galaxies were merging and forming larger structures, larger galaxies with different forms and shape, forming stars at different rate, some more efficiently than others, it really changed the picture. And I like to keep in mind of that image of the first galaxies as really small and then slowly merging through gravity process and then creating larger objects. And this simulation is actually very nice because we can see those blue dots that are the star forming, the red one, the reddish colors are the older stars as it aged, and the gas is in green. And we can see that in some areas only has gas, some area as mostly old stars mixed with gas, and some areas are really actively forming stars, which is at the core of what I study. And we have all these galaxies nowadays with different mass, different shapes, different history of stellar formation from the past. And some are really odd shaped because of like very recent interactions. So that's what our universe, the local universe we basically are swimming in, is like right now. So I'm focusing on how the stars are formed, because stars are so important in the evolution process of the universe. And in galaxies, we have star formation everywhere. In a lot of cases, those star forming regions are very massive. Some can be very small, forming just a few stars. But most of them are quite massive, and they form a lot of stars. And through what we observe in the galaxy, or in the nearby galaxies, where we can see very well what's happening, we can see those clouds of gas that are slowly transforming stars, and even confirming what we observe through simulation, we can see that this process of gas collapsing through gravity and forming stars is not necessarily super efficient, because only a fraction of the gas is used to form stars, but it's still efficient enough so that it's happening on and on in a lot of places in galaxies. And what I'm interested in is really studying this in real good details. So in this simulation, you see those sync particles, those little white particles emerging from the densest filaments in that interstellar gas cloud. And of course, in this case, there's hundreds of them. And although we cannot see the differences between those sync particles, they do produce stars of different mass, which have slightly different properties, but most importantly, are formed through the same mother cloud of gas, which had very specific abundances and density. So this is really at the essence of what I do nowadays, understanding this process in a very large, integrated fashion. Okay, so this is one of the very well-known young stellar clouds in the Milky Way. We can see the stars here, the gas, the warm gas around it. And this is just another simulation showing that sometimes it can be very violent and create clouds that are much more massive. And a good example of that is the Tarantula Nebula, which is known to contain the most massive stars known in the local universe. So what is the difference in between those two? Basically is something that is very important for me in my research. And so these clouds of, these clusters of stars that are formed through the same mother cloud have different properties. They have some massive stars and some that are just like the sun. And most importantly is those massive stars, which are responsible for a lot of the chemical enrichment in the interstellar medium. So through the processes of stellar wind, supernova explosion, they do contribute very quickly to the chemistry of the universe. And the low mass stars, like the sun and others, will contribute, but later on. And it is also very important to what I study. And I always like to show that periodic table of elements that shows which processes in the universe created which elements in the fusion process. And of course, if you focus on the exploding massive stars, you can see that the very common elements that are used in so many processes on Earth and other places are from those massive stars. So it's a cycle. There's been so many generations of stars forming elements in the past of the universe that led us to today. It's something that is very important to understand and integrate when we study cosmology and the universe at different eras. And this is why my research finds its place, and it's like a piece of the puzzle in our understanding of the universe. And I'm going to focus today in one concept that is very important to me, which is the photoionization process, and why I focus so much on those massive stars that are super important in the enrichment process of the chemical element, the interstellar medium. So what I'm showing you right now is a simulation of photoionization of a B star that just lit up in a cloud. So of course we don't see the star. You can imagine it's in the middle. And as it lights up, it starts to warm up the gas. And a lot of the very energetic photons that are emitted by massive stars, and only massive stars emit enough of those high energy photons to be able to photoionize the hydrogen and the other elements in the gas. And so they create those bubble of plasma of atoms that have lost a couple of electrons, and depending on which atom it is, they don't necessarily require the same energy of the photons to be ionized. And so if you have another type of stars, like an O star, a little bit more massive, this process is gonna happen a little bit faster. It's gonna create a larger bubble. And it's also gonna ionize the gas slightly differently because you have a larger budget of those high energy photons to ionize some atoms that otherwise wouldn't be ionized by a smaller star. Just to give you a couple of examples, it could be helium getting ionized twice, or oxygen getting ionized 3 times, losing 3 electrons. So those are typically very like easy to observe in more massive stars, whereas if you look at a B star, they won't be there. And of course, if you compare to observation, the ionization models are quite good, just saying. And for people that are not like necessarily familiar with spectroscopy, that could be in the attendance, just to say that spectroscopy is basically the process of studying the light components coming from stars. So this is just to show you different stars from the most massive to the less massive one. And their spectra can be more energetic, showing more energy in the blue or high energy photons for very massive stars, whereas for lower mass stars, they are likely to be more red. So studying them with spectroscopy gives you so much more information about them. And of course, the gas is different. So you will essentially study the signature coming from the gas that is warmed up in space, that is ionized by those stars. And what you will observe are what we call emission line. And depending on the atom, depending on how ionized the atom is, it will produce different emission line with different color or different energy, if you want, and observe that in the spectrum. Since I really like to compare things with Hawaii, you've been probably in contact with those phenomenon around you just by looking at the neon light that contains a gas that is lit up by the electricity in those lamps. So depending on which gas is in your neon light, it will lit up in different colors. And of course, when you look at the rainbow, it's just coming from the light from the sun, which contains all the colors in the spectrum. And now if we look into a star forming region, we have different ingredients to study it. So what is really important are, of course, the stars that are kind of the energy input at the center, and the gas surrounding those stars, and the information, the physical input that you need to be able to modelize what's happening in the plasma around a star forming region contains basically information on, of course, what kind of stars you have in the center. If you have a very small cluster of stars, you might have stochastic effect because you have maybe one B star or one O star or a combination of a couple of them, but you're not necessarily fully sampling all the possible mass of the stars and massive stars you can have because that cluster is such a small one. But if you have a larger cluster, a very large one that contains hundreds of thousands of stars, then you're fully populating the mass of the stars that are contained in the cluster. And we often refer as fully sampling the initial mass function of the stars. So we have all of them. We know more or less how much O star you should have, how much B star you should have, according to some models and some hypotheses. And this is the information you get from modelizing the young stellar cluster. Then those stars produce a lot of photons. Some of them are energetic enough to ionize the gas. So we call those ionizing photon spectrum, which are inputted into the gas, interacting with the atoms, depending on the density of the atoms and the gas abundances, what kind of elements you have. They will interact, produce a lot of free electrons that are kicked out of the atoms. And those free electrons are going to bounce around, and there's going to be a lot of collision between electrons and atoms. And those collision are very low energy, like depending on the temperature in the gas, it could be of the order of 1 electron volt, more or less. But this is still enough to trigger some modification of the electron level on the ion that it's colliding with. So you can imagine having an ionized atom of some sort, then you have an electron kicking it out, and then it will slightly perturbate the very upper layer of the electron, trigger maybe one electron jumping into an what we call a unstable state, and it will very quickly come back to its normal state, emitting a photon of a very precise wavelength. So it happens often. So it's like exactly the same process that happens in a laser. So we have electrons bumping into atoms. You have those transition happening, constantly pumping electrons into other state, and then coming back down to the normal state, emitting one photon at the very given wavelength that we know is identified with that atom specific state. So this all produce those collision lines that we observe in the spectra. There's a lot of them. They are associated with different atoms of different level. And we also observe what we call recombination line, which is basically when an electron is recaptured onto an atom, an ion, to get back into the atom electron state. So that's the plasma that I study, and I need to basically quantify those information to study star-forming regions such as this one, and study its content and also the gas properties in which that region formed. And this process happens quickly. A region like that can form in a time scale of about a few hundreds of thousands of years. And then those massive stars that can ionize the gas live for 1 to 40 million years. If you include rotation and other phenomenon, they can extend a little bit their life, but it's mainly very quick in the lifetime of the galaxy. And then after that, you lose the massive stars that will explode in supernovae, and you will have the remaining stars that don't have any high energy photons capable of creating that plasma bubble that you observe and you study. So it's really something that I measure instantly in a galaxy, in the data of a galaxy. So I like this video because it shows exactly that. So you see all these little red blob that appears and disappear. Those are my plasma bubbles that are surrounding massive stars that are forming in the galaxy spiral arms here in that simulation. And so all of these star-forming regions, we can study them, and depending on how far they are, we see different things. Everybody knows really well the Orion Nebulae, which is about 4 parsecs in diameter. It's what we call a very compact H2 region. It's like some of the smallest you can have are about a parsec. So it's a small one. And just to give you an idea of how big they can be sometimes, I'm just going to show you a couple of examples in other galaxies. Now this one here is about 100 parsec, which is 25 times larger than the Orion Nebula. I love it because it's like a perfect circle. You don't have that luck all the time when you study them, but it's a good example. And then some in that image are 10 parsec. If you zoom in, you can see some blobs of about 2 parsec. And in this case, actually, this blob is not even a star-forming region. It's actually a supernova remnant. But it's just to give you an idea of the scales of those emission line region that we see in galaxies. And now let's go for larger, because they are larger ones. This is a complex that is about 1 kiloparsec in diameter. In comparison, that large bubble I just showed you would be just that thing like over there, very small. And then some are about 1 kiloparsec in this galaxy here, which is much further away. This is C628 at about 9 megaparsec. And if I keep going on this one, because I did study this galaxy in very great detail, we identified all the star-forming region and all the emitting area in the galaxies that have those plasma bubbles. And I wrote a code that was able to identify the peaks and basically separate their boundaries to study them separately. And this is just an example of 4 regions here in the galaxy. And if we just take a closer look here, and we select a tiny, tiny little one that is right there that you can barely see by eye on that image. Well, this one would be about the size of that gigantic H2 region that we just saw, about 100 parsec. And if I would put that at the scale of this galaxy and just push it further away, we would basically see a point. And for Orion, we wouldn't detect it. It would be too faint to be detected in the data. So it really puts things in perspective when you start studying star-forming regions in the farther away galaxies and even the far universe. So to add on to some issues that can be encountered when studying those star-forming regions, they are swimming into an environment that is also emitting light, and it's not necessarily what you want to study, but you need to deal with it. So they are the stellar population that emits light over the disk of the galaxy. You also have dust a little bit everywhere that, of course, your light is going through, and it changes the property, not necessarily the property, but this definitely absorbs some of the light that you would be observing. And then you have what we call the diffuse ionized gas, which is that gas that is just like in star-forming region. It's ionized, it's emitting, it's very faint, and it's there a little bit everywhere. And it doesn't have the same property as the gas in your region. So if you include it in the light you observe, and you don't correct anything for it, it's going to really affect the way you understand the physics of the H2 region. So to save the day and to enable us to study all of this and correct for all these problems that can arise through studying star formation, we use SITELLE. And as I mentioned earlier, SITELLE is the Fourier Transform Imaging Spectrograph at the Canada-France-Hawaii Telescope. It's a fantastic instrument. It does imaging and spectroscopy at the same time. And SITELLE is the name of a bird, actually, in French in Quebec. It's a local bird that we have in Canada. And so that's why the logo includes it, that little bird with the rainbow in it. So SITELLE was built starting 2010 to 2016, was shipped here for the first flight. And it was a long run. We have a large team that contributed to building it. I have to mention the company ABB Bowman in Quebec. And this is a picture of a friend of mine, Julie Madar, who was the project engineer for SITELLE. We also have people here at CFHT contributing to installing the instrument and maintaining it constantly, to which I participate. And also the team at Laval, which are not all there, but Laurent Drissen's team with all of his students that helped making sure Espion was working, and then SITELLE. And I was part of that team before moving to Hawaii. So how SITELLE works, why is it so special? Why is there such, just one instrument like that in the world, except from Espion, its prototype? So I want to show you how it works, because it's a basic concept, but very, very useful. And it really does a difference when you're observing large target, like nearby galaxies like me. And so the heart of SITELLE is a Michelson interferometer. And if you're in physics or related to physics, or if you've done a physics class, probably at the university level, you've had a lab with a Michelson. And if not, you should do it. It's super fun. But a Michelson is a very simple instrument. You have a light source that you shine through a beam splitter. A beam splitter is a fantastic piece of optic that splits the light into equal components. Some of the light goes up and some of the light goes sideways, so transmitted and reflected, basically. And on each side, on a Michelson, you have a mirror, one of which is fixed and the other one is moving. And when both mirrors are at the same distance to the beam splitter, we call that position the zero path difference. They are at equal distance. But the fun starts if you start moving the moving mirror and you change the length in between those two arms. And what's going to happen is that the light beam is going to recombine. The beam splitter is going to do its job again, having part of the light reflected and transmitted. And then you have a detector on the other side. And by changing the position, You change the phase of the light wave that will then start to interfere, and instead of measuring light, you will at some point measure almost no light coming through. And you can continue moving your mirror and build up this diagram here that we called an interferogram. That will basically show you the fluctuation of the light detected as a function of the mirror position. So SITELLE does that, and we measure interferograms with SITELLE. It might sound a little fancy, but at the end of the day, it's really measuring those patterns of interference created by the light source. And depending on the light source you have, depending on the color, you'll have different interferograms that will look differently depending on the frequency, and depending on also how many frequencies you have in your input. So if you have, instead of having one laser, like in the video I just showed you, you could have two lasers of different colors. Their interferogram would be different. The combination of the two would look like this. And you could either use the interferometer to measure those interferograms, or use the Fourier transform mathematical tool to get back into the frequency realm or the spectra. So we basically treat SITELLE data and end up with what we call spectral cubes. They are interferogram cubes, and then they end up being spectral cubes. And to enable doing this in SITELLE and really reduce the amount of noise and facilitate observation, the length of the observation, we also use filters. So there are filters in SITELLE of different width, bandpass, and it enables us to really target areas of the spectrum that are interesting for us and cut down parts that we don't necessarily want to sample to just make the instrument more efficient. And continuum light source with SITELLE could contain light in all the filter bandwidth, could contain light with some absorption line, like a star with absorption line. We would still get an interferogram that looks more like this when there's a lot of light, like a star. And then at the end of the day, you have the filter, you have the continuum source and some absorption lines. So the spectra will look like this. So you have the bandpass of the filter and your spectra inside the bandpass. And you have this for every pixels in your image, in which case it's a lot of data since we have about 4 million pixels in each images. And this is other example of interferograms, because you can sample interferograms for a very long time and get a lot of steps and measure variation of the interferences patterns. And on the side, it looks like this. If you're looking at this planetary nebulae, where you have your interferogram from 1 pixel of the image. And you can see a little bit of the effect of the air mass changing through time, which is corrected also when we analyze the data. And this is just another example of this tiny little box here, where you see this really nice interferogram for that object. And okay, so SITELLE, of course, is optimized. So unlike a very typical Michelson, like the one I showed you with the beam splitter and the mirrors and the photodetector right here, SITELLE is tilted because if we would use this, this model, half of the light would also go back to the source. So losing half of your photons in astronomy is not really what you want. So SITELLE is tilted on the side. So you have the filter, the light source coming from the sky, the beam splitter, slightly tilted. And so you have the stationary mirror, the fixed mirror, and the moving mirror. And we have instead 2 detectors on both arms of the output of the tilted Michelson. And we use both cameras to get our data. And this is just to show you a couple of images of like what you would expect in a normal Michelson is something like this, with the bullseye and all those interference pattern coming from a green laser. But since we all are tilted, we are observing slightly aside of that. So the SITELLE data look like this if you put a laser inside of it. And I also have a video to show you a laser that we use for calibration. So if you're close to that 0 path difference, you'll see the flux going to one detector to another. And if you're far away from it, if the mirror is moved very far away from it, you'll see more fringes. And as you move the mirror, you see the fringes passing from one detector to another. And I can stop it, but believe me, if there is one negative fringe on one detector, there is a positive one on the other. So this is the image of the two detectors. So that's how it works. And of course, we use that to calibrate the instrument in both wavelength and also making sure also we have the position of the mirror correctly. And I'm just going to go quickly a little bit through that, but this is our calibration process. And this is a scheme of our optical system showing the beam splitter, the fixed mirror, movable mirror, and the two detectors on SITELLE. And so we have this wheel on top, which contains the filters and an integration sphere that we use for calibration, and all the inner part of the interferograms, the interferometer. The beauty of that is that you can select your spectral resolution. So typically you can target a filter that you want to observe that it has a given bandwidth. And if you want a lot of spectral resolution, let's say you want to see very high precision on velocities, or you want to separate emission lines that are super close by to each other, you want to have very high spectral resolution. Whereas if you don't, then you want low resolution and you're still good with it. And it only depends on a couple of parameters, but mostly the number of steps that you're observing. And I probably started the video a little bit too quickly. So on that video, you'll see on the left the interferogram of 1 pixel in an image. And on the other side, it's the spectrum after Fourier transform building up as we get more information from the data interferogram. And so I'm going to let it go, and we'll see more images being taken, so more point into the interferogram. It corresponds to more points into the spectrum. And in this case, some people might recognize the spectrum of a, this is a supernova remnant, and this is H-alpha, nitrogen, sulfur 2 lines of a supernova remnant. And you can see the interferogram and the spectra getting nicely defined as time goes. So SITELLE does that for every pixel of an image. So for my science, okay, I already told you I want to study those plasma bubbles. So we need to account for things that are around it. So the underlying stellar population and dust, the diffuse ionized gas, and we want to know the property of the star-forming regions that are characterized by a lot of things. And we use photoionization model to understand that. So SITELLE enables us to look at galaxies that are in the nearby universe, close to the Milky Way, get those spectral cube, and this is a spectral cube of NGC 628, which is concentrated over H-alpha and nitrogen and sulfur. And I can see how much data has been acquired per second. So depending on the object you want, each step will have a different exposure time. It's all about what kind of signal to noise ratio you want to have. So in a galaxy like this one I'm showing you, I can tell you this was about 350 steps, so 350 images. And each of them was about 15 to 20 seconds. So it's a couple of hours of observing time. And then if I focus on some areas of the galaxy, you can see how many regions are in there and how quickly it recuperates a lot of information from the emission line coming from those plasma bubble around star-forming regions that contain massive stars. So with that in mind, in 2018, about a year after I started working at the telescope, I built up a program called Signals. I am the PI of this program, but I have 4 other co-PIs. You might recognize Pierre Martin, which also worked in Hawaii, Laurent Andriessen and Carmel Robert. Carmel Robert was my advisor as a PhD student, and we are still continuously working together. And Laurent Andriessen, also the PI of the instruments SITELLE and Espion. And Philippe Abraham is from France. So with these collaborators, we built up this project, and time got accepted. So we got allocated now about 60 nights of observing time, which is significant, to conduct this survey of star-forming regions using SITELLE. Our collaboration contains about 70 members right now, and they are coming from multiple countries, and each team have different level of expertise to help us analyze this huge data set that contains that will contain at the end of the observing time, which is in a year now, about 50,000 star-forming regions, which is a lot. And there has not be any survey conduct in this fashion before. So we are really excited in analyzing the whole data set coming up. This is an image of our workshop that was done containing about half of our collaboration in 2019. And so just diving into what we do, what is SIGNAL and why it is so important that we conduct this survey. So SIGNAL is an acronym standing for Star Formation, Ionized Gas, and Nebular Abundances Legacy Survey. We are looking into those star forming regions that are contained in different galaxies, in different environment in those galaxies. And I like to show these images because star formation can be located in the center of galaxies where you have a bunch of stars, lots of gas, lots of star forming activity. And it can also happen in some very, very remote location in galaxies. And it can really be in a quiet area where there's less gas, or if there's just as much gas, it can happen more efficiently or less efficiently. And without studying a large amount of star-forming region and really understanding how their environment affect this whole process, we will never be able to really understand how star formation evolved through the life of the universe. Just by intuition, you might think that star formation changes as a function of metallicity or chemical abundances, which would probably be a good intuition since we know those stars that were formed at the beginning of the universe were so much more massive. But when those changes start to be very small, the only way to really understand if more massive stars are produced or less, depending on the environmental factors, is to study a large sample that contains a lot of them and mostly contains all the possible parameters, all the possible environment in which stars can form, to study them all. So this is what we do. And the importance of that is that also doing it in the local universe, the fact that we have so much more definition on the formation of stars and those regions, we have more information. So if we were studying things in the Milky Way, we would have so much information about the condition in the gas, the electron, the free electron temperature, the free electron density. You can have even the dust extinction distribution. You can have abundances variation through the nebulae. You can measure the stellar mass in the center, star by star, comparing with models. So you really do have a lot of information. And if you go a little bit further away in those local galaxies, you still have some of that information, but you start to lose spatial information. So instead of having the electron temperature and the electron density very, very well pixel by pixel, you'll do it integrated over the whole star forming region, which is okay. It's better than not having it. And then you will also do the same kind of approximation for dust extinction, abundances variation through the nebulae. And then instead of seeing star by star, you will have a cluster of star that you can see, and you might be able to get its mass, but you will have to do some assumption on the initial mass function of those stars included in the cluster. And if you continue to go further away, then you can forget about some of that information. You will have global abundances of the gas, maybe still like a cluster, maybe some cluster will be merged together because you won't see them separated. And you still do those initial mass function assumption. And for the cosmological survey of very far away galaxies, you don't have anything. So Signals is there to do it at high spatial resolution. So compared to other surveys, we are really in that realm of spatial information on the regions, which is, to give you an idea, it's about 1 parsec in resolution up to 40 parsec in resolution, but surfing with a mean resolution of about 15 to 20 parsec over the galaxies we observe. And each of our observations are in the shape of a data cube. And like I was saying, SITELLE is using filters, so we don't have the whole visible spectra. We have filters, we've selected 3 of them. We have the SN3 filters that contain H alpha, nitrogen, sulfur, and we have also a SN2 and SN1 filters that contain other lines from oxygen and also H beta. So this is what it looks like. I'm going to show you a video of a data cube. This is a field of M33 with a lot of star forming regions, as you can see. And it's just one of the fields. It's a mosaic that we're doing because it's such a large galaxy. And you can see nitrogen in here, and then you can see some lines coming from the sky lines and H alpha. So this is the data I work with, but the lines are fitted using a code that was specially built for SITELLE. You might wonder why the lines look like this with the big wiggle on the side here. This is typical of a Fourier Transform Spectrograph. The instrumental line shape of the instrument is not a Gaussian, like in normal spectrograph. It is a sine cardinal function, which contains the lobes on the side. And this is an example of a zoom in of one region in that same cube, just to show you sometimes the dynamical information that is hidden in there with filaments inside a region that can have different velocities and shell and expansion and things like that. So there is a lot of information encapsulated in each data cubes. And for each of them, we have 3 of those filters. This is just one filter of that galaxy. And we have acquired already a lot of data since 3 years, but it still corresponds only to half of the whole survey. Most of our observations are actually going to happen this year, with almost 50% of our observing time being this year. And through all these data cubes that I'm showing you in the back, this is just the H alpha image. So you can see the star forming region. And we have already detected automatically with the code I wrote about 30,000 star forming regions, more or less, in this whole set. And we are intending to double this amount. And as you can see, I actually made a gradient of on this side, you have, of course, M33. You can maybe recognize the mosaic if you squish your eyes a little bit. And some of the irregular small galaxies. And then if you go on the right, we have the most massive one of the samples that have higher metallicities, higher stellar content, and some of them are more or less gas. We also have CO and H1 data for all the galaxies selected in the sample to measure the gas density. So lots of data, and this is just an example of one of them. This is NGC 6946, and if we zoom in into some of the region, you see that identification procedure that is working mostly well, identifying regions that have the ionized bubble in them. So very quickly, just saying, you know, these galaxies are not at the same distance. I was talking about spatial resolution. It's so important for signal. So with some galaxies, we have such a high spatial resolution that we can do a little bit more than some others, like this one, that are a little bit farther away. And if we would put this galaxy at the same distance, it would be so small in comparison. This is a very small galaxy. This is such a large one. And so within the signal goals of studying those star forming regions, we have kind of 2 set course for the science that can be done. And we have some galaxies that have super high spatial resolution, in which we can study a little bit more in depth some of the region. And then we have all the others that are contained in a larger sample that contain everything to do the large sample statistical study of star forming region. And each of them are studied separately in a sense, and they give us so much information. And we study not only their emission inside one of the detected region here with its contour, but we also study its profile and how the emission is changing as a function of the distance from the stellar cluster. And this is an example of a profile coming from one region that is mostly spherical. And we also categorize them in different shapes. So this is a spheric one, but we have different categories to study them. And we also study the background, the diffuse background of that region, to be able to subtract something from that diffuse background that is contaminating spectra that we study. And so this is just an example of some of the categorized identification of the region, where we have some that are spherical, some that are asymmetric, some that are filamentary and diffuse, and their specific profile. And you see some lines here that are actually associated with their size, how we define their size in parsec, and the diffuse background from each region. Our procedure is using the emission to do that, to identify them, to identify the peaks, the center of them, and also their zone, where all the pixel around the peak is associated with one given region. But it also gives us the ability to detect all sources, and then afterward maybe do a little bit more of the analysis and start identifying regions that might not be star-forming region. They could be planetary nebulae, they could be supernova remnant, and other emission line regions. And also, just to make sure that you know, this process has to be done automatically on thousands of regions. I really wish I would have time to go and identify them almost manually to do like the perfect job. But this code was built to do mostly like an almost perfect job, but there's still about 0.5% of false detection through this process. And it's actually really hard to get it lower than that. But we are really happy with the performance of the code, which enables to do that automatically. And so it really identified the background of the diffuse ionized gas and subtract it, and also what we call the limit. And the limit is defined with our ability to find the size of the region. And the size of the region is easy to identify when you have such high resolution data, but in most cases you don't. And so when you have a fuzzy bubble, to be able to identify the size of it, you need to simulate what a bubble that would be resolved would look like at that distance, and put a threshold on that size according to what you observe with the emission line. So this is what we do with the code as well. So some of the first results that was obtained through doing the pre-analysis of our galaxies is, of course, defining what we call the luminosity function of H2 region. So how bright they are as a function of their number. And this is important because it is related in some ways to, if you have enough region, of course, if you have a large sample that is statistically significant, it is related to the amount of massive stars that you have in your clusters. And so you could think that in different environments, if you have more massive stars, then you would have more luminous regions than in an environment that doesn't, that doesn't create those massive stars as easily. So one of the things that we want to do with signals, once we have the full sample, is to compare those luminosity function in different environments, different mineralisity, different stellar population background, stellar population density, and also gas density. And this can be done already with just one galaxy if you want. And you can also study, another thing that I really like is how much diffuse gas do you have around that region? Because diffuse gas is known to be related to the amount of ionizing photons that can escape a bubble, an H2 region. And so if you have a lot of those escaping photons, you will have more diffuse ionized gas, or brighter diffuse ionized gas surrounding your region. And it gives you a cue on, well, a couple of things. It can be related to the mass of the stars that are formed, because if you have such massive stars that it just lits up all the gas around it, you'll have a lot of escaping photons. But if you have less denser clouds that are forming the stars, the light will go through more easily. It can be also related to the nature of the distribution of the gas in that cloud. There's like holes, pockets that let the light go through. And by having such a large sample, it will enable us to study that in in a unique way that has never been done before. So we intend to study that component of all the regions together, and see if it varies also as a function of the environment. And still related to that, just with one galaxy, there's some very cute findings you can do. And this is the one that I published in the paper of NGC 628. You might recognize the Stromgren sphere equation, which is actually not that complicated. You need ionizing photons, the QH, to create that plasma bubble. And the radius of that bubble is, of course, directly related to that. And also some factors, including the temperature of the electrons and the density of the free electrons in your plasma bubble. And if you remember those basic class talking about photonization, if you've been lucky enough to follow them, there's two models. There's one model in which that plasma bubble is still surrounded by a neutral gas cloud. So nothing is escaping. The ionizing photons are trapped, and so you wouldn't see any ionizing photon getting into the diffuse ionized gas and things like that. But in some cases, the stars ionize completely that bubble of gas, and the photons, some of them are still ionizing energy, are able to escape that and are like basically free to go into that lower density medium around that cloud. And when you observe those regions, instead of measuring what would be close to the Stromgren radius, their radius is smaller because they've ionized everything there. And then some that would have been used to ionize more gas are just free to go. And so when I compared the luminosity of all the regions observed in that galaxy with their given radius, their size, I obtained these, and I just tried to play and compared with the Stromgren sphere model using different density and temperature for the electrons. These are some curves that shows typical values that you could get. I would say that those are pretty extreme, but are still plausible. And this round here is, of course, the most likely values for a star-forming region, an H2 region. And what is nice here, you have those yellow dots that are my regions, which have also a very high diffuse ionized gas background, like I was talking about. So there's probably a lot of photons escaping and ionizing the background gas. And you can see they're not necessarily following a given trend of those Stromgren model. They are more luminous and smaller than what they are likely, what they would likely be if they would follow a normal curve of the Stromgren values, the Stromgren radius models. And so it is highly likely that those regions are actually what we call those density bound nebulae that have ionized everything. They're smaller, they're brighter, they have a lot of massive stars, and there's a lot of escaping photons that are triggering that diffuse ionized gas emission around them. So just by using one galaxy, we were able to do all of this, and I can, this is just a forecast of what signals we'll be able to provide as extra information on those star-forming regions and how they affect their surrounding. And I'm really visual, I'm an observer, so I like to show comparison in videos. One thing that I like to do when I get a data cube is to look through it, look visually at the data. And this is a blink of two emission line measure of the O3 atom and ion and the H beta line. And if I just zoom in one region, I'll show you here what it looks like. But what I want you to see is, you see that some regions are just appearing and disappearing as this goes. You can see this one here, there's one right there, and right there. And this is actually due to the content of those regions. They're in a very small area of that galaxy, so very likely having the same abundances and metallicity of the elements. But some stars are more massive than others, like the O stars and the B stars, and so their spectra is also different. Showing more oxygen-free line for those more massive stars that create a series of phenomena in the plasma that really enhance the O3 line. And it can be, so that for that reason, can also be just a more massive region versus a less massive region. It can be a younger H2 region, which still contain O stars, versus an older one that had O stars those stars explode in a supernovae, and then you have more B stars remaining. And it all is related to how we sample all of these phenomenon. It can be stochastic sampling of the masses of the stars inside the cluster. So I just want you to notice that, because when you study star formation, star forming region, all of this can happen. To be able to tell if something you observe is related to a physical property or a physical phenomenon, you really need to distinguish all of these aspects of each of the region. And by building signals, by building this huge sample of 50,000 each region, you're able to smoothen these effects that are stochastic sampling. The age of the region are going to be smoothened because you're going to have a bunch of young ones, a bunch of medium age, and a bunch of older ones. And you're also going to have all sorts of masses and all sorts of stochastic sampling of the initial mass function. So you need these regions, a lot of regions, to be able to go beyond that and do physics with them, and eventually tackle the problem of the initial mass function of the massive stars in different environments, which is very important in astronomy for cosmology and local universe as well. And I'm almost done. I hope I'm not talking too much. I have like a few slides left just to show a little bit of the other methodology that we use to analyze the star forming regions and signals. So we both use the whole sample as a tool to study population of star forming region and study how they evolve through different environments. Then we can also use single H region spectra and study their property, their metallicity, their temperature, their stellar content, and things like that. And we can also study them spatially when we resolve a single region in 2 dimensions, and we can study the distribution of the emission through the nebulae, which also enable other physics. And we have the processing that is ongoing. And as I said, we have different processing for the low spatial resolution and the high spatial resolution targets, which include comparison with ancillary data coming from other instruments and telescopes. If ever you're interested, all of this is on our website. And we also have a division of the science team that tackle different problems and analysis within the data set. And just to finish on a good note, so I'm from Canada. I love nature. This is me when I was young. This is me when I was in Canada about a week ago. So nothing has changed for me. I'm still, I love observing the nature, and I'm still doing it at the telescope. I think doing it in nature in Canada and where I'm from probably led me to be a better scientist and a better observer. And all the details we observe in nature that makes me probably a better fisherman and a better hunter are important when we do science. And the same little things that tells me there's a moose around and which helped me succeed as a hunter is helping me nowadays with signal and what I do with the data and signals to be really ready to look into all the little details of this. And I don't know what I'll be discovering. I hope I will discover good things that will be useful for all of our community. There's so much thing we still have to discover. I'm just going to finish showing you the cloud cam on the Mauna Kea, and hope you enjoyed the talk. And I will be looking into the chat for the first question, but feel free to think about new ones and put them in the chat. I'll be looking into it. Thank you so much.
Oh my gosh, Laurie, thank you so much for such a multifaceted talk. I mean, I love the way that you've linked the science into your experiences in in Quebec and your hunting and just the link with nature. It's amazing. It's I've really enjoyed it. So thank you very much.
Thank you so much. And all these little details like that I presented at the very end, like how massive is a star, how massive is a cluster, what is the variation of abundances, could there be ages discrepancy, all these little details I've learned through observing and just looking into the data and figuring out, oh yeah, maybe there's something that I haven't thought about or didn't include it yet in my analysis. And I still believe I'm using all these skills nowadays.
No, that it's interesting you bring that up because, you know, a lot of research astronomers, they just take the data from the telescopes and analyze the data, but you are more of an observer. And I think that's been more of a link to our members because we're all observers. I mean, depending on where we live, whether it be in a light polluted area or a darker area, you know, our fascination started with just looking up and seeing the night sky. So
Yeah.
it's interesting. I remember, you know, I did a video on the 1991 eclipse of the sun that passed over Mauna Kea, and I'll always remember this video this fellow sent me of the shadow of the moon just leaving the summit there, and it was just this massive black blob, but you could see it moving, and it's like that had to be an
Wow.
impressive thing. And you know, I think there is definitely the need for someone like yourself to not only, you know, just take the data. I mean, I remember my astronomy professor in second year who just had reams and reams of output on his desk, and he just had to go through this. And I mean, it's just like, oh my God, how are you going to do that? But just to be able to take the data and look at the pictures and analyze them, you know, there has to be that kind of intuitive analysis of what you're doing. So it's very, very interesting. I'm sure we have some questions. I wanted to ask you one thing, and I've always been interested in the fact or the question about multi-generational solar systems. And that is, you know, I'm thinking, you know, I go back to Cosmos in 1988 with Carl Sagan and him talking about the sun's siblings and where they are now. And then after a generation or two of stellar systems, is there a way to identify those in galaxies that we see, something that's the remnant of other systems that have sort of died and spewed all their material out into the galaxy and started up a new system?
That is such a good question. I can start on this one without necessarily having like a one answer quick, but you know, one thing that I like is to picture things the way they were in the past. That's why I was showing you these videos, just to be in the right mindset. And if you would imagine like a solar system from the past coming like with a younger star or a star that was born in a younger generation before the chemical enrichments of the universe started to kick in, and what did it look like? And what I can say is that stars that are at lower metallicity, that are formed from generation that are prior to the solar system, if you would pick a star like the sun, same mass but lower metallicity, you'd still have more ionizing photons because you don't have the screening from all the metals into the atmosphere of the stars that blocks things and scatter things out and absorb some of it. So it would be a small difference, but it would still be there. And so you'd have more ionizing photons that are not necessarily good for life. And they would definitely impact the atmosphere of the planets in a different way. I don't know how, and I'm not a specialist in chemical atmosphere, like a reaction in the atmosphere of planets, but that would be, of course, a strong effect. You could also think that the radius at which you will find the planets will be very different. And I'm sure there's some simulation out there about this, but I'm not aware of it. It would be like my first guess.
That's fine. That's what you're paid to do, right? Make some guesses. So James Webb is going to be in the news in a few months. And I'm wondering if this is a project that you're looking forward to. Is there something that James Webb can, you know, you can get onto the James Webb observing list to look at something in specific?
Yeah, you know, I've been involved in some of the James Webb preparation program by default because I'm also supporting an infrared camera at the CVHD. And so supporting WIRCam or infrared camera, I've done some tests using the observation, the very one I took 4 signals using the infrared camera just as a, you know, a support data for some of the science we're doing. And we're checking at how the James Webb Telescope would help tackling the measurement of the Hubble space constant through the cosmological time. And so we were able to show that with the spatial resolution of Hubble, the James Webb Telescope, over galaxies that are hundreds of megaparsec away, we would be able to fit Hertzsprung-Russell diagram, color diagram of those stars, and therefore identify carbon stars that are candles to measure distances very precisely. And then once you have those distances, you can really have precise measurement of the Hubble space constant. And that's really fantastic to me. And for my science, just to loop back into SIGNAL, I am using infrared data right now that have the resolution that I need, because I don't need more than what we have on Earth to do this. But you could think of eventually maybe launching an instrument like SITELLE in space. And so once we have the SITELLE, like the equivalent of SITELLE in space in combination with the James Webb Telescope, it would be so much more powerful, because I could do SIGNAL, but at a very larger volume and go up to 100 megaparsec. Right now I'm limited to 10 megaparsec. So you would have a larger sample of all the star forming region in that volume. It would be great.
Yeah, no, it sort of, it suggests a real, expansion of the potential for taking specific. I mean, I remember back when MOST was launched in 2001, 2002, just to look at variable stars, and now, a potential Canadian mission just to go out and look at these specific things.
Yeah.
It seems that,
and I see some of the questions that like looking back through the chat, I see some of the questions I didn't answer during the talk.
Well, that's fine. You want to go back through them? That'd be great.
Yeah. If you don't mind, I really want everybody to So I read here, how do you get velocity curves of galaxy when they are seen above their pole? I showed one early in the talk. It's really, sometimes it looks like they are seen by the pole, because they look like almost spherical. Even NGC 628, the one that I use a lot, that big one, looks like it's face on. It is face on, but it's actually 21 degree off.
As seen at legacy.com in the third week of September 2021.
Yeah.
Actress Jane Powell.
Oh, sorry. So I guess, so that was like already 21 degree off. And so with that very small angle, we can still measure the velocity curve of galaxies.
Okay.
And and so the translation of SITELLE is the bird nuthatch. I hope I'm saying it right. I guess it's the English word for it.
Oh yeah, the nuthatch is a wonderful little bird. So I'm glad I know now the Quebecois name for our little nuthatch. So SITELLE. I'll have to tell my wife. Say SITELLE.
Yeah. When operating, roughly how much data is being acquired per second? So I think I answered that one. It depends on the image and the object. Sometimes it's one image per a minute, and sometimes it's one image per a few seconds. It really depends on the strategy and what kind of object we're observing and how many steps we're taking, the spectral resolution. It's all kind of all intertwined. But we can define that very easily with the tools we have for planning observation. Could you comment on the recently published 3D model of the star-forming regions of the nearby Perseus Taurus supershell obtained from Gaia data? Oh my God, I didn't have time to read it. I'm so ashamed. I hope it went out during my vacation. Like, it would give me a really good excuse, but I'm not sure because I haven't read it. So if you can forward me it, I would love to read it and just give you a feedback on it. It would be my pleasure. But I know Gaia's potential to do that, because it's resolving each stars, and their velocity, and of course you can modelize their ionizing spectrum very well. If you have their ionizing spectrum very well, then you can input that in a very well built photonization code and simulate the gas that you have around them. So that would be fun. But yeah, definitely for one of my students maybe in the future. Oh, what attracted you to pursue astronomy? That's a good question. I think I've always loved astronomy. For me, picking physics was like a challenge. I loved all science, but physics was the most challenging to me. And I like that. I like to be challenged in life. So that's why I picked physics. And astronomy, it's just because it's larger than us. Everybody loves astronomy. And I like the fact that I can still talk about what I do with anyone, young and old. And they still can kind of understand what I do. And I think that's why I picked astronomy. What is the closest star forming region to Earth? Orion would be probably a good candidate, but we are still like, even the sun, we are kind of, I've read a lot about the environment of the sun, and we are kind of inside an old supernova bubble, a very old one. So in the very, very past, there had been a supernovae, and we are still in that kind of fuzzy diffuse ionized gas remnant from that. That is very low level, but yeah. So that would be the closest emission line region to the sun. We're kind of embedded in it. But most of any area of galaxies are, in a sense. And okay, after the software identified this region, do you then go back to get further detail? Yes. So I showed you the software that I used, that I wrote to identify region, identify boundaries, and then look at the profiles. We look at the profiles, we can identify their emission and mass and size and luminosity and all sorts of things. But we have to go back and forth a couple of times, because some information you get from integration of their spectra, some information you get from their spatial information, and also some you get from other data, from the infrared, the H1, CO, UV. And so we have to go back and forth, because each of them have different spatial resolution. And so we always need to analyze things so that they can be compared at different resolution. What kind of computational power is available for your research? I am lucky. I have a lot of help at the Canada-France Hawaii telescope for computational power, but I am also using CanFAR, which is like a program of the CADC. So they have clusters of computers that are available to the Canadian community. And so if you have a program that requires a lot of power, you can request to have your own virtual environment created for you at the CADC. So this is what we use for the collaboration as well. All my collaborators have their password. They can log in into CanFAR. They have their virtual machine. They can run things. It's fantastic. And all the software is installed and updated by the Signal team to make sure that they are using the latest tools, and they don't have to do it. It's fantastic. So if you're interested, you can ask me. I can forward you contacts from the CDC that can help you with that. Yes, the publication from Signal. So we have the description of the survey that is already published. It's published. And I still have a couple of papers coming from my students that are working on some of the analysis tool of the survey. So you will probably see my name with Carter Ria. He is from Montreal. He's been working with me on machine learning technique to analyze the spectra in a very quick way, comparing with the photoionization database models and so many other things. But you can look up into his publication, his latest publication. It'll give you an idea of what we're doing with that. Okay, you still need more observation nights to get more numbers. Yes, we need more data to have a statistical sample. Yeah, it's after a year of observation, when we finish, how much time is it going to take for you guys to see the results from Signal? It's going to take a couple of years, I can tell you. I was saying 4 million spectra per data cube. We have 3 data cubes per field. We have about 40 fields with SITELLE. So just to give you an idea, you can you have like 4 million spectra times 40. Each of them are identified, treated, and then we have to check. We're not going to process that in a black box and not make any verifications. So it's going to take a little bit more time, I got the good news a month just before leaving for vacation. I got funding from NSF to hire a postdoc working with me at CFHD. So I will have my postdoc to help me do that in the next 2 years. So hopefully quickly, but it will take time. It's a large survey, and we have a large team, but there's a lot of data. So it will take that. And as soon as some of it is available, we're going to probably leak some of the pre-processed, parameters that we are calculating online, so that other people can do their own research with it. Sorry? Oh, okay, I thought it was a question, sorry. And one last question, are star forming regions that are not amenable to your approach? I'm thinking of the Eagle. Yes, that's such a good question. I didn't talk about that. You know, when I'm categorizing the region depending on their morphology, it's really hard to study some H regions that are mixed with each other. They're not a bubble. They have stars that are forming and they are mixed with others. Some are fused with other H regions. Some have supernovae currently exploding with a supernova remnant in them. It makes analyzing their photonization spectra so hard. So of course, out of these 60,000 regions, some of them won't be able to be used. And we have ways to, unfortunately, remove them from the sample because it's just too complicated. And we are a survey, so we're doing things, we want things to be done uniformly. So if I would start one case by one, those very specific hard region to study, it would make the whole process very uneven. So unfortunately, we have to take them out. But that's the strategy. If you have any suggestion, I'm all ears. And as I was saying, it was the last questions. I can see now that there's 2 more. Okay. As the Starlink satellite had an impact on your observation, we've had some targets that were already in the lane of the satellites. And for those, I can tell you that about 10% of our images had trails. We only take them again, and we have to take the data again if it's passing through the object, fortunately. But it could correspond to about 1% to 2% of the observation. The Starlink, it's the same. I have a SITELLE run coming up in 2 weeks. I can give you an update because this is an evolving situation. Yeah, I'll let you know if ever it comes, but I think it's going to still be a fraction, a few percent, and things like that.
Okay. One last question.
Okay. Our star forming region, oh, wait, I'm passing one. I have to be fair. Do you also make data available for citizen science or take public help? It will be probably in a shape where some people can use them once I publish the first output of the survey. But for now, it's still in a very complex form, which I would say you would have to have a lot of courage if you're a citizen and you want to launch yourself into that. Nothing is impossible, but so maybe with the first data published, it will be possible. Yeah.
Okay.
And yeah, if that's all the time I had, I can probably yeah.
Oh my gosh!
Answer back.
Thank you very much for answering all those questions. Those are great questions. It's all right. There's one last one here, but are star forming regions interesting to planet hunters, or do they prefer established star systems?
I think they prefer established star system, but I have to make an ad for one of our instruments at CFHT that is not SITELLE. We have a planet hunter at CFHT, which is called Spirou, like the French cartoon character Spirou. And if you go online, you'll see they have a survey, and it's a high resolution spectrograph targeting stars nearby the sun, mostly low mass stars that are more likely to have planets which can harbor life. And they are observing them constantly to measure radial velocity variation of the stars and see if they dance because they have planets around them. So more to come on Spirou, but definitely not for star forming regions with massive stars like the one that I'm studying.
So, Laurie, I always like to end a talk like this to really ask an unfair question to the speaker. But so you're relatively, new in your career with an amazing capability on an instrument on a large telescope. So like 10 years from now, what kinds of things are you hoping to be able to, or questions are you hoping to answer with, improved technology, and maybe all this based on CFHT, but I wonder, but you've got to have sort of a sort of wish list on, your best answered questions.
Yeah, that's such a good question. I always have a lot of hope for new technology in future. Like I know that a lot of people are working so hard on different instrumentation, including like the, high cadence stem sampling instrument that are going to help us study physics process that happens like in fractions of the time that we've been able to see before. And also with larger telescope, being able to see further away, or being able to see better things that are just by the Earth. For star formation, because it's such a narrow field in astronomy. There's so many things that needs to be discovered, and I have my wish for signals. I know that we will probably be helpful in giving a picture, like a global picture of star formation, and give people that do cosmology a tool to study galaxies that are not resolved and super far away, and maybe study how this star formation process has influenced the universe, and it's going to impact other fields for sure. But if I have a wish on the next future, I hope to be surprised. I hope that I've thought about everything and we'll make discoveries that are just coming from our sense of observation, things that we just fall on. So that's my true gift, that my good sense of observation will lead me somewhere.
Well, you've been so generous in sharing with us your time and your passion on the work that you've done. I every now and then I open up a book that I don't know where I got it from, but it's from the 1890s, and it shows galaxies as something to be internal to our galaxy, and the kind of thing that what they what our understanding was back in the late 1800s, and then to look at where we are now, it's a quantum like huge leap, and it just seems to be that every decade, after Hubble changed everything, but then after that, our understanding of just the universe, and then to be able to take these specific instruments and or large telescopic instruments and do the kind of work that you're doing, it's really amazing. And it just proves that you can't predict the future, because who knows where we'll be, but we'll be all watching your career to see where you take your study, because I always find it so exciting to talk to someone who shares with us the latest, like this is the latest stuff that I've been doing, but then to continue on and see where you're going to go with this. And we're really thank you. We thank you for sharing this time, and we appreciate that. And we all are amateur astronomers, and we love the science, but I always have appreciated the fact that as amateurs can deal with professionals and share these things, and it's just so cool. So thank you very much, Laurie, for sharing your time.
It was my pleasure. It was fantastic to be connected with you guys remotely from Hawaii. Love the questions, and thanks a lot for the nice comments. Yeah, and if you have any other question, you can email me.
Okay, aloha.
Thank you, Laurie.
We're going to be
Aloha.
on your doorstep one of these days, I'm for sure. Thank you very much. Thank you.
Bye. Aloha.
Aloha. Yeah, your weather's a lot nicer than here, I'm sure. And for everyone here, just to finish up, so thanks everyone. This is our September speaker night. We'll have a potpourri in a few weeks, and we'll Swapna, if you're on board, do you want to talk a little bit about our October speak at all, or Neil, are you linked in? Because we've been busy working on program.
Yeah, sure.
Okay, great.
Is Anil still there? I think he just left. Okay.
We have
So
a huge team of people working on getting speakers like this. I hope you people appreciate all of the work that goes into this. I mean, Laurie's talk was phenomenal. And we have even a better talk in October. And Swapna knows all about it.
Yeah, thank you. Yeah, Laurie's talk was incredible. You know, we are very lucky to be able to be connected to CFHT for sure. Next month, we're going to hear from NASA, a lady in NASA, Michelle. She's going to come and speak to us. We're still finalizing the topic on that front. So really looking forward to the October speaker night. Again, this is Anil found the speaker, so thank you, Anil. The next talk after that is the November talk, where we're going to have the RAS John Reed, who's going to come and speak to us about some big, it's great for beginners, so telescopes, certifications. You may have seen him if you've attended the Explore the Moon or Explore the Universe RAS series that ran very recently. He and Jenna actually ran that series. So we're very lucky to have John, and he'll be dialing in from Nova Scotia. So as Randy was saying earlier, we're attracting the side benefit of COVID has been that we've been able to bring people from outside the GTA into our meetings. So Hawaii was represented. We've got somebody from the United States next month, and we've got Nova Scotia the following month. Thank you, Randy.
That's great. Yeah, thank you. Yeah, so, I mean, our program committee is working 24/7 on these things, as you know. So it's a great opportunity for us to bring these people in, and we just if you have suggestions, then that's a great opportunity for us to to look into things, because we're going to be on Zoom for a while, which is it's not too bad. It'd be great to see everyone face to face, but it looks like we're going to be online for a while. Okay, so that's generally it. I'm going to suggest that we close off for the night. It's getting on, but thanks again to Swapna for setting up our speaker tonight. Laurie was awesome. And we have a potpourri coming up. So if you have any talks that you want to present for the potpourri, we are definitely interested in that. And as I say, we're moving on. If not in person, the Mississauga Center is moving on in a virtual way. And I'm really happy with the way things are going. We have a great council and a great support team in the membership. So let us know what you think. But otherwise, if there are no other comments tonight, I'll end the meeting.
Thank you, Randy.
Thanks, guys. Great.
Hey.
Thank you, Randy. Nice seeing you, Swapna.
Yeah. Thanks,
Bye.
everybody. Hi,
Thank you
Francine.
so much.
Good to see you.
Yeah.
Good night. Thank you very much. It was awesome tonight. Thanks
Yeah.
to Swap and all the organizers. Great job.
Great. Thank you.
Thank you, Francine.
Maybe we should meet on a patio somewhere or something. You want to do that? That'd be fun.
Yeah, I guess it's getting cooler now, though.
Yeah, well, I guess that's good for transmission rates, but anyway. Okay, everybody, thanks. And we'll see you soon.
Bye-bye.
Okay,
Bye.
take care.
Bye.
Bye.